Let me introduce Guido. He's Guido Appenzeller is the CTO for Intel's data platform group, where he's responsible for technical direction and pathfinding across the data platforms portfolio. Prior to joining Intel, Guido was the chief product officer at Yubico, where he focused on product development and strategy to aid in making strong authentication truly ubiquitous. Guido was previously the CTO of the cloud and networking at VMware, where he helped define VMware's multi-cloud strategy. For VMware, Guido was co-founded Big Switch Networks and Voltage Security, where he was leading both those companies as CEO and CTO respectively. From 2008 to 2010, Guido was a consulting assistant professor at Stanford, and he holds a PhD from Stanford University. All right, take it away, Guido. Welcome.
Fantastic. Well, I'm excited to be here today. I want to tell you a little bit about what we're doing with P4 at Intel. But actually, what I mostly want to talk about is what particularly excites me about P4 right now. And let me switch over to the slides here. So I always like to start, when I talk about technology, to trace this back to first principles, right? And if I look at sort of the overall IT landscape right now, right, where are we? Well, we're sort of in the middle of the cloud revolution, right, which is a big thing, right? It's only the second time, I think, in the history of all of IT that we're fundamentally changing the model, how compute is delivered, right? I mean, we went from mainframes and workstations to PCs, like the client-server model, and now we're going from PC, client-server to cloud and mobile. And I think we still haven't, as a research community and as an industry, fully digested all the ramifications of what that means. And if you think about this for a second, right, the architecture of how you build a cloud versus how you build a classic traditional data center initially were almost the same, right? You had same kind of silicon, same kind of servers. And then we start seeing a divergence, right? Specifically, the hyperscalers started architecting their systems in a fairly different way. And if you think about this for a second, that actually makes sense, right? If you were an architect and you would build a hotel versus a single family home, how you would design them would be very, very different, right? If in my home here, I probably wanted to be easy to walk from the living room to the kitchen, right? Or to my to the laundry room, wherever my washing machine is. In a hotel, that's very different. In a hotel, I don't want the guests that occupy the guest rooms to go into the restaurant kitchen. Those are cleanly separated. There's an area for the staff, right? And there's an area for the guests, and then they shall not meet. And we're now essentially seeing the same trend happening in cloud architecture. And the place where that manifests itself most is actually the NIC, or the Smartnic in these systems. So if you have here on the slide, on the left side, this is how a classic data center was designed, right? I have a CPU with a more or less Smartnic. And say if this is the data center of a bank, the bank would manage the CPU, the bank would manage the NIC, the bank would manage the entire system plus the workload that runs on it. So everything is one tenant, and that keeps things fairly easy. On the right side here, that side, we have somebody using a public cloud. So in the public cloud example, we're actually now seeing a split of the compute elements, where the compute elements from the infrastructure provider, the cloud, and the compute elements that run the software from the tenant are different pieces, right? And the way how it usually works is that there's a SmartNIC running on these systems. On the SmartNIC, you have all the infrastructure software from the cloud service provider, and then the actual CPU is completely freed up and can be rented out at maximum profit, right, by the CSP to the tenant. And even the hypervisor in some of these cases actually is not run by the cloud providers. If you look at, for example, what VMware Cloud is doing on Amazon, right? In that case, you have the hypervisor from VMware running on the CPU, and there's the entire system is managed by Amazon just through the NIC. So this is the architecture that is getting very common in the cloud. Most of the large clouds today run with some flavor of that model. These SmartNICs have a set of common functionality. They are typically the root of trust. They're used to provision the initial workload on that host. They're used for storage offload. They're used for network offloads. These things are quite important because for two reasons. One is it allows you to rent out more of the CPU capacity, right? So it helps the bottom line. And the other one, it actually avoids all kinds of noisy neighbor problems, right? So your long tail in terms of jitter and latency looks much, much better. And there's different architectures. You know, we have a lot of eFPGA-based ones that are being used today, as well as some dedicated silicon Smartnics that have these functions basically built in. And they use a broad variety of protocols. So in my personal mini statistic, I believe out of the top 8 large hyperscale cloud providers in the world, there's not 2 of them that use the same storage protocol, for example. So it's a very, very heterogeneous world. Everybody does it a little bit differently. And you know, that's how the big clouds compete with each other, right? And that's great. We as Intel, we want to support them in doing that. So why does all of this matter for P4? Now, these NICs obviously have a packet processing pipeline. And it's an absolute no-brainer to express that in P4, right? It's a lot better than creating yet another proprietary C API. I can, if I use P4, make use of the existing tool chains that are already available for P4. And it's actually a huge win for the cloud service provider as well, because they, if they ever want to switch to a different SmartNIC vendor, they now have a general abstraction that makes porting that software much, much easier than it was before, right? So having a generalized way for the packet processing makes a lot of sense. And you know, a number of vendors are moving in that direction of using P4 for that. Now, I would like to take this one step further, though. So I want to throw out a little challenge here for the P4 community and see if you can help me with that. And what I'm really getting interested in is storage here. So if you look at it right now, the #1 function of these SmartNICs is actually storage. And let me illustrate a little bit of what they're used for and why this is really exciting from a cloud service provider's perspective. So if you have a system, you know, over here, you know, we have on the left side, we have the CPU. On the right side, we have the SmartNIC that manages the system on behalf of the cloud service provider. And this server today is often diskless. So there's no disk attached to it anymore. Now let's assume I want to rent out this server. Somebody wants to run a hypervisor on it. And for that, they always need a disk to, you know, boot from and store their data on. So what I would do in this case is that basically my control plane will talk to a storage service in the backend, right? And say, and also talk to the SmartNIC and say, hi, you know, I need a new volume here. And then basically a volume gets created on the storage server, you know, over here. And then that same, and then what the SmartNIC does is that basically it takes that volume information and uses the PCI Express bus to create a new virtual hard drive, right? Typically using NVM Express, you know, which is the fast SSD interface. So suddenly a new virtual drive is popping up, you know, on the PCI bus that the operating system can recognize and tie this in as a hard drive, you know, that for that system. And once that's established, I can then start booting from that hard drive and use it, and you know, add more hard drives if I want to, and so on. So this is all nice, but we want to do this obviously with a very high performance. So ideally, when we get packets in and out from that storage service, right, over here, this storage service, then we would like to do this without ever having to go on the slow path. So we'd like to stay entirely on the fast path and never move into software. And what do we need for that? Well, we need a pipeline, right? We need something that takes these packets that come from the storage service and, you know, basically do, you know, basic operations, right? You know, right now we can't do it with P4, but hypothetically, you could imagine adding this to P4. So we would take the packet, we decrypt it, we authenticate it, you know, maybe parse the protocol header. I may need some, depending what protocol it is, some JSON parsing or something like that. Maybe it's all binary, then binary is fine. Compress, uncompress it. And at the end of the day, I move it over, you know, into to the CPU, either via PCI Express bus, or in some cases, I may be able to even write it directly to the cache of the CPU. So I could do this very fast transfer of the block so that from the CPU's perspective, there's really nothing to do. It's just, you know, a block of storage arrives and nothing is ever done in software. So, you know, here's the thing that would really excite me for the P4 community. If you could give me primitives in P4 that would allow me to express this complete pipeline, you know, that manages the storage service, that would actually be a huge step forward for, you know, getting a more generalized portable interface across these SmartNICs that everybody's building these days. You know, just to give you an idea, I think actually in a typical cloud data center, we have a lot more of these SmartNICs than we have switches, right? So while if you look at currently, you know, with P4, there's this beautiful vision of taking a single, you know, a single runtime contract, a single abstraction that allows me to program the network across the entire network. You know, if you look at the top clouds, I think there's a healthy debate to what extent that is necessary or not, right? There's some clouds, I think, which completely agree with this view. There's some other clouds that say, look, you have to over provision so much, your leaf and your spine. Anyways, it doesn't really matter. Move all the smarts to the NICs. But currently, every single cloud agrees that these Smartnics are important. That's an important control point. So that's I think actually to some degree, from my perspective, probably the more exciting use case for P4 than the switches are. So that's that's my plug here for if there's anything we can do to make that an even more front and center, I think it'd be really exciting. And if you had this, right, you could then actually your runtime contract between your control plane and the individual parts of your architecture that execute, that execute the pipelines could even be more general, right? Suddenly, this wouldn't just be about, quality of service and networking and telemetry. This could be about things such as creating virtual disks and moving storage around. So it would almost be more like a cloud orchestration contract as opposed to just a networking runtime contract. So that was my plug here. I want to end with a couple of quick words on Intel. At Intel, we're big fans of P4. I think many of you know the Tofino switches and that they support P4, and we're continuing to heavily invest in that software ecosystem. I think what we haven't talked about much is that we're also working towards enabling P4 across our entire SmartNIC line and our FPGA line of cards. You'll hear some announcements about that probably later this year, but it's an area that we're actively investing in, and our goal is to really have P4 running across everything, switches, different architectures of SmartNICs, and as well as software in a software accelerated way on our general purpose CPUs in the future. And with that, I say thank you, and it's I think back to you, Larry.
Great. Thanks a lot. So let's see. We're getting a few questions come in, so I'll turn to some of those, but just before I do, so extending P4, do you see, it's an obvious starting point. It's there, it's used in switches, and it's a natural thing to try to do. But there's a risk, I think, of extending it in ways that it becomes so general purpose that it might have well have been any other language, and maybe you've lost some of the value of P4. Do you have any thoughts about that tug of war?
Yeah, no, I think it's a fair comment, right? I don't think the idea is to extend to general purpose language. I think, look, P4 for me really shines in expressing pipelines, right? And if I look at what do I need to do with incoming traffic, that's a pipeline for me, right? If I look at service mesh, that's still kind of a pipeline for me, right? The unit is no longer a packet, so it's not a packet pipeline, granted, right? So that's a little, I think, deviating, from at least the very original idea of P4. But there's packet reassembly anyway, so these things are complicated, right? So, but I mean, I think anything that can be expressed as a pipeline in a hardware type of setting, right, or in hardware, virtualized hardware, like if it's an abstracted hardware, like that's fine too. But something that still looks like a silicon hardware type of pipeline, I think that to me seems fair game.
Yeah. Yeah, so it's fair game. So I think the thing that would be challenging, and I'm not a P4 expert by any stretch, but I would think that this maintaining state on a per flow connection kind of basis would probably become the challenge there. But
that obviously depends on the architecture of the particular silicon that you're using, right? I mean, look, effectively, I would say every cloud service provider today keeps track of at a connection or at least volume level, right, of all the storage traffic anyway. So I don't think the amount of state on the NIC would actually change, right? I think it's more a question of what I use to express that state.
Good, right, very good. All right, so let me turn to some of the questions that people have been entering in. One from Blake is that he imagines that Western Digital has already gone a long way towards achieving the storage idea that you talked about with Omni Extend. I'm wondering if you have any thoughts on that.
Look, I don't know that particular technology.
Yeah.
Look, again, I think the system that I described is what's being used today, right? So the system architecture, that's not something that is novel, right? That's something which I think probably is more 80% of the top clouds, 85% of the top clouds are using today.
Right.
I think the question for me really is there a better way to program that other than with proprietary APIs, and can P4 help here? I don't know what if OmniExtend implements P4, that I haven't heard.
Yeah, I don't know that whether it does. So your use cases tended to be towards data centers, and kind of naturally so. Have you thought about the edge a little bit more? Which, I mean, on one level, it's a smaller data center, but it might also have a lot of access technology built into it. And
Yeah.
if any, what's your thought on Smartnics in that domain?
No, I think they're needed in both cases, right? I mean, the edge is a really interesting market, I find, because it's not really one market, frankly, right? It's a selection of verticalized use cases, and they're all a little bit different, right? I mean, the edge box that gets strapped to a telephone pole for the antenna on top just looks different from what somebody needs in factory automation, which is again different from a payment terminal in the supermarket when I go shopping, right? So it's really this collection of verticalized markets. But look, at the end of the day, they're all data centers. At the end of the day, I think many of them, well, all of them will be managed through central control planes, and many of them will be tightly integrated with clouds. So I think many of the architectural principles there are just equally valid.
Yeah, yeah. So there's some questions around. I'm just going to kind of lump them together as a little bit of why P4? Why isn't it being universally adopted? There are other things that people could be doing. Do you have? And I know you're not necessarily saying it has to be P4, but can you comment on P4's front runner nature here and what it's going to take to become more universal? If you see any path forward. And there could be a lot of divergence here.
I think P4 is the clear front runner. I don't know if I'd have to implement a packet pipeline. I'm not sure what else I would use, frankly.
Yeah.
Right? I mean, I could invent my own proprietary Guido API, but it's not clear how that brings mankind forward, right? So I think if today I have to pick something, I probably want to pick a standard, and P4 seems to be the by far the best choice there, right? For expressing these kind of pipelines. What will it take to get it more widely adopted? I think a lot of that has to do with industry dynamics, frankly, right? It's about vendor A versus vendor B kind of things. But that said, I think that'll probably just delay timelines. I don't think it'll change the outcome.
Yeah, yeah. So all right. So let me throw in a straw man, which would be ePPF and XXD as a way of expressing pipeline-like match action rules, but with another origin coming in from the OS. Is that an attractive option?
Sorry, I'm not that one.
XBPF?
Oh, I mean BPF. I see them.
Or I'm sorry, eBPF. Yeah.
BPF. Yeah. No, I see them both as valid and complementary, right? I think. They could long-term, could you do long-term everything with one of the two? Maybe, right? But I see them more as complementary where, if I wanted to do something purely in the operating system, I probably lean more towards eBPF. If I have more of a silicon target, I lean more towards P4. Yep.
If you would like to spend some time answering some of those questions in their live, that would be great. But let me move on to the next speaker. Thanks, Guido.
Awesome. Thanks, Larry.